latch is basically once you put a value, it gets locked, right? Like a door latch. Okay, so that is why it is called a latch. And we will start with that as the first basic storage element called the R-S latch. You will find many book references where they are also called SR latch. Okay, so don't worry. R stands for reset and S stands for set. So we are going to design a circuit, or we are going to look into the design of a circuit that can store this value q or q bar. Of course, q bar is the complement of q on our demand, right? So if I look at this slide, we said that no, not useful without a control mechanism for setting q. Okay, so if we do not have a control mechanism for setting q, this is just going to be useless, right? Who is going to write q and q bar? That is the reason we are having some kind of a control called set and reset, which is going to control the value of q in the circuit. Okay, so this is a example implementation of this SR latch. Don't worry about this. It's just not always NAND gate. You can always do it using NOR gates. But in this particular case, let us go forward with this implementation. Okay, so S here, as I told you, stands for set and R stands for reset. And you have not a cross-coupled inverters, but these are a cross-coupled NAND gates. Okay, so there is a NAND gate on the top. This is one NAND gate, NAND 1. This is another NAND gate, NAND 2, and they are cross coupled with each other. Okay, it was same as the inverter, right? If you look at the inverter diagram, there is not much difference apart from the fact that instead of the NOT gate, we are using a NAND gate, and the NAND gate is taking an additional input S and R. Okay, this is the only difference. Otherwise, it is a cross coupled inverter, very similar to that, right? Also with a NOT sign. Okay, so these are cross coupled NAND gates. Data is stored at Q, and inverse of the data is always going to be available at Q bar. S and R are called the control inputs. This is the inputs through which you can control whether you want Q to be 0 or you want Q to be 1. It is very simple. You will come to it. All the combinational logic knowledge you have is useful here. Okay. So there is an quiescent or idle state which is both S and R are held at 1. So if you have S and R, right, which are both held at 1, we have to see what it means in the circuit. There is a set state if S is drive S to 0, keeping R at 1. So if you make S equal to 0, Q is changed to 1. Okay, so let us see. If you have S, this is your set thing, set input. Let me write it here, set, and this is your reset. This is kind of important. You have to write down the circuit and sort of practice yourself to understand how the control flows, because there is always a feedback in this kind of a circuit, right? So what goes in again goes into the gate, and sometimes it comes out, some things get changed and so on. So you need to actually patiently write down the circuit or draw the circuit on a piece of paper and see how with time things change. Okay, so there is set and reset inputs, and if S is put to 0, so set, this is put to 0, what will be the output? If it's an AND gate, right? So it is irrespective of this particular input, AND gate output is going to be 0, so the NAND gate output is going to be 1, correct? So if S equal to 0, that means we are putting the value of Q to 1. Okay, Q is equal to 1, and if you have Q is equal to 1, this is taking care of this particular line. And R, if you remember, if you see here, drive S to 0, keeping R at 1. Okay, so this R is equal to 1. R is not being changed at all, right? Because that will change the complete equation. Okay, So if R is kept at 1, right, in that case 1 and 1, if it is an AND gate, the output is to be 1, output will be 1, but it's an AND gate, so the output is going to be 0. So Q bar is equal to going to be 0. Okay. So remember this particular operation. If S is equal to 0, you put Q is equal to 1. It's like setting the value of Q. Okay. Setting the like S equal to 0 means setting the value of Q to 1. Similarly, if you do it the other way around, I can just do it for your clarification. Let's say I use a different color. In this particular case, S is set at 1. Okay, S is set at 1, but R is set to 0. Okay, this is basically saying that you are resetting the circuit. Okay, R is set to 0 now, while S is at 1. So in that case, as you can understand, 1 0 you hear in this lower part of the circuit, the output of the NAND gate is going to be 1, right? Because 0 is here, doesn't matter whatever is there on the other input, the AND gate output is going to be 0. So the NAND gate output is going to be 1 for the green case. Okay. So in that case, the Q bar is going to be driven to 1. And following the same logic, this is going to be 1. Just follow the color, because the previous case was done using blue color. The current case is being done using the green color, right? So 1, and here S is equal to 1, so that output is definitely equal to 0, right? S equal to 1, and in that case Q is equal to 0. Okay, so these are the two things that we can use to change the value of Q using the set and reset inputs. If you want to set the value of Q to 1, then put S equal to 0 holding R at 1. If you want to reset the value of Q to 0, put reset to 0 and set to 1. Okay, just vice versa. What happens if you do the first thing, right? If you put both of them are held at 1, right? That is kind of important. So if both of them are held at 1, what does it do? Okay, that's an important question. We need to understand that. That is called the quiescent or idle state. Okay, so you can try this thing out, not a big deal. Let's say S is equal to 1 and R is equal to also 1. Okay, so now you can simply see the pattern here, right? So what would have happened in this particular case? We are saying that the value, the system is in idle state, which basically means the value is going to be retained. Okay, so how is the value going to be returned? You can do a quick check. So this is 1, right? And this is also at 1. So now it simply means that if Q is equal to 1 and Q bar is equal to definitely 0, that has to be stored. So case 1 could be, let's say this is case 1, Q is equal to 1. Okay, so if Q is equal to 1 in the first case, because Q could be 1 or 0, right? First is Q is equal to 1. So in what is the input here? Because Q is equal to 1 here, this is the first thing. 1 and 1 is going to be how much? The output is going to be 0, right? This is the first thing that I am discussing. And if it is 0, then 1 input is going to be 0 here, right? This is again the first stage, first case, right? So the output is going to be 1 only, right? So S equal to 1, the one more output is equal to 0. So 1 and 0, the AND gate is going to be outputting a 0, so the NAND gate is going to output a 1. So Q is equal to 1 is retained. Not only that, Q bar is equal to 0. That is also there. What is the other case? The other case would be the circuit was originally not holding 1, the circuit was originally holding a 0, right? So this is the second case. Let me write it in this way. This is the second case. The second case is Q is equal to 0. In that case also it is very easy to see that 0 and 1 will be retained. If S and R are both equal to 1, both equal to 1 means it is going to act as a memory element. So just for the clarity, we will anyway do it. If Q is equal to 0, so then instead of Q equal to 1, this is the second case, Q is equal to 0. So the output, as you can see in the second case, is going to be 1. And if the output 1 is here is 1, this is again the second case, this is 1, 1 and 1, NAND output is going to be 0. Right? So there is no fighting among the different inputs and outputs. Okay. So this is going to be stable. So if you have S equal to 1, R equal to 1, this is going to be holding the existing value of Q in the memory element, which is more like acting like a storage of a bit. If you wish to change the value of Q, if you want to set it to 1, you have to put the set thing, set input to 0 and reset to 1. Okay. If you want to do the other way round, if you want to set the value of Q to 0, you have to drive the reset to 0. Okay. So just remember this. Whatever is the value of S equal to, if you want to do S equal to 0, that puts Q to 1. If you want to do R to 0, it puts Q to 0. Mind that the other inputs has to be set to 1. Okay. If both of them are 1, this is memory. Okay. This should be clear. There is one more thing that is mentioned, we are mentioning it here, that R and S should never be 0 at the same time. Okay. Again, you can see what it means and so on. We are also going to give you a small demo about how this works if both S and R are 0 at the same time. So in none of the previous use cases, we saw that particular input, right? Because if you write a truth table, right, with S and R being the inputs, you can have this kind of combination 0 0 0 1 1 0 and 1 1. Out of them we saw this was acting as a memory. Set is equal to 0 was used for setting the circuit, or Q is equal to 1 setting. If you want to use S equal to 1 and R equal to 0, this is same as resetting the circuit, Q is equal to 0 reset. There is one more combination 0 0 which is still remaining, and suddenly we are saying that S and R should never be both 0 at the same time, and you need to investigate why, right? We will investigate why. There will be some problem that you can figure out yourself also. If you can pause the video and try it out yourself, that would be nice, right? So this is a truth table, that is what I have just shown you on the top. So 1 and 1 is Q previous, which is same as memory. Okay, so this is your previous output. Okay, so this is already clear. This is about setting and resetting. Q is equal to 1 and 0. So S equal to 0 means this is setting the circuit and this is resetting. That conventions sometimes change who calls what reset and set and so on. So but structurally the shape of the circuit is just going to be the same. Okay, so now the point is that you can investigate on this particular part about what is meant by forbidden state or why it is forbidden. So I'll give you a hint here, right? This one is already done. I would ask you to repeat this exercise on your own to get a more clearer understanding. So now comes the case where I want to put both of them equal to 0. That was the question. Okay, so here S equal to 0 and R equal to 0. What will happen? You need to kind of understand. You can take some time, and you all know about all these NAND gates, and this is a NAND gate. So just by looking at the circuit, you can see there is something wrong. if S and R are both equal to 0, they are both NAND gates. So you can guess the outputs, right? And try to see that whether the outputs match with our original claim Q and Q bar or not, right? Because otherwise it will cause a problem. So we'll demonstrate that. Okay. So this is S R, same circuit. Okay. Other test cases have been already checked. Okay. R equal to S equal to 1, R equal to 1, S equal to 0, R equal to 0, S equal to 1. Now what if R equal to S equal to 0? So this is the fourth case. So now both of them will be 0, 0. Okay. So Q and Q bar with both settled to 1, which breaks our invariant Q is equal to Q bar, right? I mean, Q should not be equal to Q bar, right? That is basic assumption. But if you have 0 and 0 in both of them, you can very easily see that is they are just not of an AND gate, right? AND gate, one input 0, it is definitely going to produce 0, and not of that is definitely going to produce a 1. So this is very easy to see that this is going to be 1 and this is also going to be 1. So this is one of the basic violations of our agreement, that we are going to always store Q and Q bar. Okay. The other thing is, yeah, so this is the circuit, right? So now if you consider some kind of a transition, so if S and R transition back to 1 at the same time, Q and Q bar begins to oscillate in between 1 and 0 because of their final value depends on each other. So this is again a transient state or a metastable state. That is what I was mentioning even for the cross coupled inverters. Okay. So this is okay now. S equal to 0, R is equal to 0, although it has violated the condition, let's say that is fine. Okay, Q and Q bar are not equal, are equal here, which is a violation of our assumptions. But let's say we deal with that. Okay, we are okay with that for now. The other problem is this metastability, where S and R, suppose they have to transition back to 1 now, because that will be required, right? You cannot keep the S and R at 0 indefinitely. It might be required because we want to now use this particular circuit as a storage element. So I might have to change both of them to 1. So let us change it to 1. Okay. So if both of them now change to 1, let us see what happens. So now this is going to be the case, because if both of them are 1, right, 1 and 1 is 1, and if you take a NAND of that, this is going to be 0, right? Similarly, if you take 1 and 1 here, the output is again here is expected to be 0, right? This 0, right, comes here, and then 0 and 1 is going to be 0, right? And if you do a NAND, this is going to output a 1, right? And this one again goes to the other side, and then this 1 will be this is partially 0 and 1, right? So the output is 0, so this is 1 going to the other side, so this is going to be 1 now anyway, and 1 and 1 is 1, the output is now 0, so this is going to be 0. Okay, so there will be some fluctuation in the value. It depends on which one converted to 0 first or which one converted to 1 first, right? Because two of these NAND gates are going to have, let's say, two different speeds, and this 0 might be delayed. This 0 might come out first, or this 0 might come out first. Depending on that, the values on the lines will change. So this will require a little bit more attention. I can reiterate this particular discussion. That is what I have done. I can do it one more time. Once we have this cross-coupled this thing, right, as well as these values are 1 and 1, and they were changing from 0, right? So earlier there was a different value, and now they want to change. So in this particular case, 1 and 1, they should output typically as 0. Both of them should output typically as 0. Okay, but the thing is that this 0 comes here it is replaced, right? Or the other thing could be that this is computed first, right, and this is unaffected, right, and this is changed to 0, right. In that particular case, this is no longer going to be 0, this is going to be 1 now. Okay, so as you can see, there is an ambiguity. Okay, that is what is called the metastability state. If this one comes out first or this one comes out first, based on that, q and q bar are not going to be of the same, the q is not going to be a unique value. It depends, it can either be 1 or it can either be 0, and there could be some amount of fluctuation that goes on. Okay, so this eventually settles depending on the variation in the circuits. Okay, this is actually going into the hardware. So all these NAND gates might not be exactly the same. Someone might have a higher latency or a propagation delay, it is called, or someone can have a lower propagation delay. Depending on that, one is going to settle down earlier than the other, and based on that, the final output is going to change. Okay, so I would recommend you to draw two circuit diagrams like this. In the first case, you can assume that the first NAND gate is faster. Okay, if the first NAND gate is faster, in that case you will get a 0 earlier. Okay, and this is not going to be the case. You get a 0 earlier. So NAND 1 is faster. If you NAND 1 is faster than the NAND 2, this is, you are going to get a 0, right, and this is going to be striked off. You are going to get a 0, and 0 and 1 is again 0, and NAND output is 1, and this is what is going to happen. The other case is, so here q is equal to 0 and qr is equal to 1. Okay, as you can see, that is settling down to these values. The other case is that, let's say they are changing, but this one is a bit faster, right, NAND 2. So in that case, this is going to produce a 0. Okay, and if this produces a 0, then you can see that this is also going to be 0, right, 0, 0, this is going to be 0, this is going to become a 1. Okay, so then q is equal to 1, then q bar is equal to 0. Now which one to take? Is the same circuit. Okay, so there is a definite ambiguity that is created if both of them are set to 0. Okay, I would ask you to try it out one more time to really understand that why S and 0, R and S both being 0 is called a forbidden state. Okay, so I have analyzed it. I would recommend you to do it yourself. Okay, so if you want to write down the Boolean expression for an R-S latch, this is going to be a function of two inputs S and R and two outputs Q and Q bar, where Q and Q bar are complement of each other. Okay, so as you can see, this is written here. So S dot Q bar, so this is your output Q, right? So this output Q, or we can typically call it Q next, because for a sequential circuit we typically deal with the next output as a function of the current outputs and current inputs. Okay, so what is going to be the next thing? What is going to be the next state of the circuit? So Q next is a very common expression which is not used in case of combinational circuits. Combinational circuit doesn't matter what is next. Next will depend on next inputs, nothing to do with current inputs or current outputs. Okay, so we will come across this term next many times. So Q next is, as you can see very easily, this is S, this is Q bar, and you basically have a NAND of that. So you have S dot Q bar, which is the AND operation, and you take a bar of that, which is the NAND operation. Okay, and what is again Q bar? Q bar is a NAND of Q and R. This is R. If you take Q and R and pass it through a NAND gate, you get Q bar. So S dot Q bar whole NAND, a whole not, is equal to S dot RQ not. Okay, RQ bar basically, and then bar of this. Then you can apply De Morgan's law internally. So it is RQ whole bar becomes R bar plus Q bar, and this actually becomes S bar plus R bar plus Q bar whole bar, okay, which could be further simplified to S bar plus RQ. Okay, this is a Boolean expression now that could be used to find out Q next, given that you have what is the value of S, R and Q. Okay, the value of Q could actually be the current value or the previous value. If it is a current value, we are trying to predict the next value. You can try this thing out, right? You can try your various values and try to see whether things make sense or not. Just mind that for R and S both equal to 0, you are not permitted to use that kind of a configuration in R-S Latch. Okay, that is something that you need to respect. Apart from that, if you are using S and R as 1 and 1, you can test out that Q prev is being maintained, or currently you can say that Q next is Q current, however you want to define. If you are using S equal to 0, right, and if you see S equal to 0, it's very easy, right? If you put S equal to 0 comma R equal to 1, as you can see, it's an OR function, right? So irrespective of the value of R and Q, doesn't matter, it's an OR function. So S bar is equal to 1, so S bar is equal to 1, so Q next is equal to how much? 1. It is going to happen, right? No other option. The other option is S equal to 1 and R equal to 0. So if you have S equal to 1 and R equal to 0, S bar becomes 0 and R is being ANDed with Q. Does not matter what is the value of Q. R is being ANDed with Q and R equal to 0, which means that S bar plus RQ, which is Q next, is equal to how much? It is going to be 0. Just validating. You have to be in a habit of validating this kind of expressions and make sure that you understand that. Okay. And the other option is both of them are set to 1. So if both of them are set to 1, so S is equal to 1 and R is equal to 1, S bar becomes 0 plus R into Q, but R is equal to 1. Okay, then it basically becomes Q. So which is basically Q next equal to Q, and this Q is nothing but the current Q. Whatever the value that was currently being held by the circuit, that is Q. So Q next equal to Q. It won't change. Okay. So these are the three operations. You should not put the value of R equal to 0 and S equal to 0. So that is not going to be, as I told you, that is going to result in a metastable condition or a transient condition or an oscillating condition. That is not something that could be, that is anticipated by an R-S latch. Apart from that, if you use the other configurations, it will work fine. There are three states. Either you can either set the circuit, reset the circuit, or hold the previous value. Okay. So this is what I have explained right now, but I will ask you to do it one more time. Right? What are the different possible values of Q for the different configurations of S and R? Okay. So please make sure that you understand this R-S latch. This is something very, very important, and this is going to be used later. We are going to not directly use R-S latch, but we are going to improve upon R-S latch. For example, how can I remove this forbidden state, right? I cannot have a circuit that has a lot of these forbidden states and all. It becomes kind of messy to deal with these kind of circuits, right? We want to make these things better and build upon R-S latch. Okay. So this is not something in this course of knowing about all these latches. Later we are going to look at flip-flops and so on. There is an inherent continuity. Okay, this is not like I have learned about multiplexer, then I forget about multiplexer and start learning about decoder or encoder. In this kind of a scenario, there is a linearity and there is a continuity. You have to know R-S latch very well in order to know about the next thing. For example, I'll talk about a D latch and so on. There are some issues. We are going to look into flip-flops. Then we are going to look into JK flip-flops and D flip-flops and things like that, right? So there is a continuity involved here. I am repeating it now that please understand this kind of latching and the feedback mechanism, particularly if you are confused about it. Talk to your instructors and see that how this feedback mechanism works, whether you are really understanding it or not, because this concept, if it is not clear, right, the sequential circuit, the entire sequential circuit is going to be dependent on feedbacks. Okay, so the current feedback is being actually sent to the next time, right, as an input. This is important to understand how it is working. Okay, so I'll stop here. The next thing that I will study is this gated D latch. Okay.